Hello everyone, welcome back to my channel Deep Understanding of Research Paper. Today in this tutorial I will cover the paper Improving Gender Identification in Movie Audio using Cross-Domain Data. This paper is by Rajat Hebar, Krishna Somandeepalli, Shrikant Narayanan from USC, University of Southern California. So the overview of the tutorial is going to cover the overview of the paper, the introduction to gender classification. Then we will see the data sets used in this paper. Then we will see the methods introduced in this paper. Then we will see the experiments, and finally we'll see some results. So the overview of the paper is like this. So this paper addresses this problem of gender classification in media data like movies or in like YouTube videos. The important part in this paper is called something called voice activity detection, which is one of the important block which is needed before gender classification. We will see why is that. Then this paper uses algorithm called transfer learning, which is basically some sort of learning from some pre-trained model, something similar to fine tuning of some model. So we will see what is the approach and what is the pre-trained model they have used for gender classification. Then we will also see how they have used bidirectional LSTM for voice activity detection, which is called VAD. Then this paper also shows the effect of using cross-domain data. For example, using some studio recorded data or telephonic data and trying to see how it performs on movies data, right? Then this paper shows we can achieve this gender classification up to an accuracy of 85% uh, 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 using this approach. Then they have released some the data set which they have annotated manually for movies. They have released it for 4 different movies, and that data is public and you can use it for your research purpose. What is gender classification? So gender classification from audio is basically identifying the gender, whether it's a male voice or a female voice from an audio. And you can think of this thing as simple classification problem which can be solved just by using the pitch feature as a input to some model. Or you can set a threshold of pitch value and say the audio is female voice or male voice, because usually female will have a higher pitch compared to male. But in this case, in the case of movie, it is not as easy as just putting a threshold on a pitch and classifying the audio into male or female category. So the main point here is that movie data will have a lot of background music and a lot of noise. It's edited audio. So that is the reason simple features like pitch cannot do discrimination between male voice and a female voice in movie kind of data. So if we build a gender classification model using some clean data, and if we try to apply the same thing on the movie data or a YouTube kind of data, this will not work because of the background music and edited audio content. So as I said, pitch is not going to help us because of various background musics and noise. And for this reason, we need some very robust features which will give which we can use to classify the gender. So robust in the sense those features should not vary depending on the background music, or should not vary depending on the noise content in the audio. So those robust feature, if you can get them from somewhere, or if you can train a system which will be robust to those kind of noisy conditions, then we can get a pretty good accurate uh, gender classification system. We will see how this is achieved in this paper in the coming slides. Next we will see the data sets introduced in this paper. This is one of the important point in this paper, because as I said, this The name itself suggests that uses cross domain data. So cross domain basically tells if you are doing something, or if you are testing the model on some data, and the training could have happened or would have happened on some other data, in the sense the modality of the data may be different. For example, we could use YouTube data for training, and we can test how it will transfer on movie kind of data. Or we can use some studio recorded data for training and test it on movies data. So this is some sort of cross domain, because the distribution of these two data sets will be different because of the recording condition and because of the noise level, all those parameters. So we will see what is the algorithm they have used, and what is the data set they have introduced to capture these, or to get this robust feature, which will give us high discrimination on gender classification features. So for data set, they have used many. They have. I'll tell you there are three different data sets here. First one is for VAD training. VAD is basically voice activity detection. So we will need a voice activity detector, which will do a very good job of separating audio from music, because audio from non-speech. You can say non-speech and speech. Basically, speech is something where there is some spoken data, and non-speeches could be silence, or it can be noise, or it can be background music, right? So we want to train a model which will give me a segmentation of speech and non-speech. So for this, we can't use some openly available model like OpenSmile. OpenSmile will still work, but the accuracy will be very low, because OpenSmile will maybe using some sort of energy feature, where it will classify low energy frames as non-speech and high energy frames as speech. But in our case, this noise also will have higher energy, so they will get classified into the non-speech part also. So that's why we need a robust voice activity detector, which will segment our audio into speech and non-speech. So as I said, speech could be the spoken data, and non-speech could be non-speech is something which is nothing, not like speech, like music, background noise, or silence. So for this, we don't have any kind of data where we can use a bigger data, basically a large data, which we can use for VAD training. So we have a small data set which has around 8 hours of data, but we need what these guys have done is they have applied a small technique where they have got some weekly labeled data. So the weekly labeled data is obtained by taking this 95 Hollywood movies released in 2014. So basically, these Hollywood movies are the movies which will have transcript, which are subtitles. So the subtitles will have the timestamps, and it says from what time to what time there is spoken data, and so what we can do is we can simply use a forced alignment method, and we can get the speech part and non-speech part just by using these subtitles. So this is done using a toolkit called Gentle. Like this, there are many other toolkits. There is something called Montreal Forced Aligner, which is also one of the best forced alignment toolkit. So this forced alignment toolkit Gentle will do audio alignment. Where there is text, it says this is the speech part, and we can just say okay, remaining is non-speech. So this is the data. This data is kind of weakly labeled because there is no manual interruption, or manually it's not tagged uh, as a voice noise data or speech data. So it is some sort of weakly labeled data, which we can say okay, this is pretty good for our VAD training. So we'll take that data for training the VAD. So basically, we have, after doing force alignment on all these 95 Hollywood videos, we get speech data and non-speech data, which we can use it for voice activity detection training. So that's one data set. Sorry about that. So second one is we need a data set where on which we can evaluate our gender classification and our VAD classification, VAD algorithm. So in this paper, they have not done extensive experiments on VAD. They have done some experiment, but they have focused more on gender classification. So for gender classification evaluation, they have used this data set, uh, which is available freely, which has this VAD timestamps, or which has this voice activity detection labels. So basically, they have uh, labeled the audio data into speech and non-speech, which is voice activity detection. But for gender classification, we need uh, male female tagging. Basically, we need to annotate the data. Annotation in the sense, we have to for every sentence we have to tag that as a male voice or a female voice. This is done manually for these four movies. These movies are Kill Bill 1, Saving the Pirate Ryan, then I Am Legend, and The Bourne Identity. These four movies, around 8 hours of data. After annotation, they get around 180, 128 minutes of speech for male voice and 22 minutes of female voice. So these we can use it for our evaluation of the model. And these performances of in this paper, whatever the results we show is those performances are measured on this data set. So we have around 2 hours of audio for male to around half an hour of audio for female. So using this data, and for the same thing we have VAD, which is voice activity detection segmentation. And and to train our gender classification, we need some data set. So this data, whatever we showed in the previous slide, this is for evaluation. So how do we train our gender classification model? We need some data set, but there are, as of now, there are no open source data which will there are I mean, not open source data. There are data set like Wall Street journals and like this page kind of data set. But for this kind of movie gender classification, which will have a lot of background music and noise, there is no data set. So what they have done is they have taken this data set called audio set, which was released by Google in last year, which is published for audio event classification. So basically, it's an audio classification data set. It has around 600 classes, and they have basically taken that data set from YouTube. So the YouTube data and movie data, the distributions comes a little bit closer. It may not be exactly similar. Means we can't directly say whatever we do on YouTube data will transfer very well on movie data, but they are close because YouTube data also will have background music, noise content, and so what they have done is from the audio set data set, out of these 600 classes, they have taken the classes which are named like male speech, man speaking, female speech, and women speaking. So they have crawled all the videos from YouTube which are tagged as male speech, man speaking, female speech, and women speaking. And after they crawl all the data, they get around 47 hours of data for male and 21 hours of female voice. So this is pretty good data for training any deep model. And we'll see the algorithm used here. That is one data set, which is audio set, and they have also second data set, which will have a different distribution compared to the movie data, because audio Wall Street Journal is does not will not have background music and noise content. So the data set is around 15 hours of data, and they have around the 7,000 utterance, 42 male and 41 female speaker. So this data is so what basically these people have done is they want to see how these the model we train on one domain data, and how does it transfer very well on another domain data. So they want to see this comparison of how what is the performance we get if we train a model on audio set data, and what is the performance we get if we train a model on WSJ data. So, and obviously our intuition says we should get a better model if we train on audio set and test it on our movie data, and accuracy should be low if we train it on WSJ and test it on the movie data. So we'll see those results in the coming slides. Now the method. So the method basically, as we know, it has two parts. So one is VAD training. So VAD basically is a voice activity detector. So voice activity detector, we want to train it with our movie data, which we got it from those 94 Hollywood movies data, and we get the labels using forced alignment of subtitles with the audio. And for training this gender classification model, so we use audio set and the WSJ data. So basically the models are like this. There are two models here. One is for VAD, one is for gender classification. So for the VAD, what we do is we take the voice data and non-speech data too. So the voice data we take and we segment it into 10 millisecond frames, and we feed this to an BLSTM. We extract the feature, which will see what is the features and dimensions of the features. Then we will feed it to a BLSTM VAD. So BLSTM VAD is basically a series of BLSTM and feed forward layer, and at the end they have this classification layer which will do classification of binaries, ones and zeros, and tells if this 10 millisecond window or 10 millisecond frame is a voice frame or a non-voice frame. And that is the voice accreditation model. For gender classification, we use something called audio set model or audio set VGG-ish audio classification model, which is basically a pre-trained model, which is a CNN model taken from Google's pre-trained models. And that model basically will have it's basically a audio classification model which will take around 1 second of audio segment and classify into one of the 600 classes. But the important thing or most important feature about this model is this will give us noise robust, highly discriminative features of audios at the last layer, which is below the softmax layer. So if we can extract these features, which are some sort of high level features, we can use them to train another classification layer, or another we can fit another classification model like a small neural network or some sort of SVM. And so that will help us, that is called a transfer learning. So basically we take this data, which is speech data. We don't take the non-speech data, we take the speech data, feed it to audio set pre-trained model, which is a convolution neural network, and we extract this high level feature, which is 120 dimension feature, and we fit a new classifier on top of that. So we fill the details in the coming slides. So those are the two models which we want. So what is voice active detection model? So we have this voice active detection model, which is a BLSTM network. So basically it consists of RNNs, and it's a bidirectional RNN, and on top of that we have fully connection layer and with the rectified level limit, and at the end we have this softmax. So input to this model is going to be log mill features, log mill features, which are of 23 dimension, which are of dimension 23, and we take 160 millisecond segment, which will have around 16 frames, and we 16 frame, basically we have 15 context frames. One is the middle frame which we want to classify, and we feed that into that 23 cross 16 dimension matrix into BLSTM. After that, the output of it will go to FC layer, then one more FC layer and another FC layer, and then finally we have this sigmoid layer which will classify our audio into one of the two class. This is voice activity detection. Basically the output is voice or non-voice frame, right? So that's what we want. And after we train and the features are extracted over 25 millisecond window with 15 millisecond overlap, basically we get 10 millisecond in the middle, right? So that is voice activity detection model, and the training is again done using normal SGD. Then second model we want is gender classification model, and as we said, this is going to be trained using transfer learning approach. So basically we take the VGG model from audio set, and this will take 64 male filter bank coefficients extracted for 0.96 second, which is almost 1 second segment, and that is some sort of matrix. And if you feed that matrix to the CNN, pre-trained CNN, which will give us a 128 dimensional vector. This is high level feature. right? So that feature we are going to take, which is sometimes called bottleneck feature. We take that feature and we feed this to a new model, which is again some convolution layer, or again some deep neural network, and finally we'll classify that into one of the two classes. So the VGG model, which is taken from Google audio set model, which will take, as I said, it takes 96 cross 64, 96 being the time 0 to 96 being the number of frames, and 64 is the feature dimension, and that goes through multiple convolution layer, and fully connection layer output is 128. That goes as input to this new model, or which you are filtering on top of this VGG model obtained from audio set. Finally we'll do the classification, right? So that is about transfer learning for gender classification. Now we'll see the experiments. So basically, as we said, we train this model by LSTM WAD model, voice aggregation model, on the 96 Hollywood movies data, and which we obtain using forced alignment, and we compare these results of by LSTM WAD with state of the art WAD model, which is again RNN model, and we'll compare it with the OpenSmile toolkit, because that also has a WAD API. Then all the evaluations are done with gender classification models. Gender classification models are evaluated with ground truth data, which is ground truth WAD model, which is what we obtained from those 4 movies data set, and we also evaluated with by LSTM WAD. And as we said, the evaluations are done with those 4 Hollywood movies, and we finally compute some unweighted accuracy as a performance measure, and also we calculate the area under curve, right? So there are 4 different experiments in this paper. So you can see here there are 4 methods: B1, B2, B3, and proposed model. So B1 is basically a baseline one, which we are going to train using WSJ data. The features we extract is MFCC, and the model is GMM model, not transfer learning model or not any deep neural network model. Basically we train a GMM, a Gaussian mixture model, which will classify our WSJ, which is trained on WSJ data, and we test it on our own data. Then the second experiment is called B2, which takes WSJ data, which is the training, and does the transfer learning, which is extracting the high level feature, which is 128 dimension, and feeding a new deep neural network. So that is second baseline. Then we take the audio set data and train a GMM model using MFCC feature. That is baseline 3. And finally we take this audio set data and use the transfer learning approach and test it with our data, which is Hollywood data, 4 movies data. And basically intuitively, what we assume, what we think is, since our data, the evaluation data basically matches the distribution with the audio set, because the audio set also has a lot of noisy data, and this model, the final model, should be better compared to any of the other model, we will see. And also we expect this model to be the worst model, because it is WSJ, which is a clean data, and it is a GMM model, and our testing data is not similar to WSJ, because our data has a lot of background music. This doesn't. So this is going to be the worst model, and we have to see how these two model will perform. So basically our intuition says this should be the worst and this should be the best, and we will see what happens to these two, right? So those are the experiments we want to conduct. Now we will see the results. So first we will see the results on by LSTM WAD. So since we have trained a WAD model, voice actor detection model, so we will see the accuracy. So we have our training done on 94 Hollywood movies data using subtitles as a forced alignment. Then when we evaluate it, so we get 66% accuracy and 41% precision, recall, and EER of 0.4. So as you know, EER should be lower. So if you see, the OpenSmile gives around 0.4 EER, equal error rate, and this is the state of the art model, which is by Lenher, which is an RNN model, which gives us around 0.13 EER, which is good compared to the OpenSmile model. And our model, which is a Bayesian model, actually has ER of 0.25, which is not better than Lenher, which is the state of the art model, but this is again has accuracy almost similar to um, uh, the state of the art model, and but it has a recall of 0.63 and precision of zero point 0.8, right? And F1 scores again, this is good, right? So this is the WAD model which we have trained, and this is the results. Then we'll see the results on gender classification. So basically the results are calculated using the Oracle WAD, which is the state of the art or which is the ground truth uh, WAD annotations we have, and we also calculate the accuracies using the BLSTM WAD. So basically, since we have to do VAS accreditation before we do a gender classification, so basically they have tested it with Oracle WAD, which is the ground truth WAD, and they also tested with their own WAD model, which is BLSTM WAD. And as we know, the what is B1 stand for? B1 is basically GMM model trained with MFCC data, trained with WSJ corpus, and we can see here it is around 87 or 87, around 87% accuracy, and area under the curve is around 0.90, and so that is with VLSM WAD, and if they use Oracle WAD, they get around 74%, right? And B2 is, what is B2? B2 is nothing but our uh, our WSJ model trained on uh, WSJ model trained on it's a transfer learning model trained on WSJ data, which gives us around accuracy around 86% unweighted accuracy, and area under the curve is 0.92. And the third model is audio set data, but it is trained using it's trained using GMM with MFCC feature. It gets around 88%. And finally, we have audio set data trained using transfer learning method, gets around best accuracy, which is 0.93, with the area under the curve of 0.97, which is the best, right? And these are the result. And as we know, as we can see here, we get very good accuracy on our test data, which is a movie data, if we train a model using audio set with transfer learning, because transfer learning on this pre-trained model will capture these robust features, or will capture these will give us these high level features which are very robust to noise and music, right? And thanks for watching this video till the end, and if you're not subscribed to my channel, please subscribe, and thank you so much.